Jesus. Good afternoon, everyone. How is everybody doing? Had a good weekend? Oh, that's good to hear. As long as the answer is like, what weekend? Um, so today we are continuing through the topics, and today we will do a little exercise in writing a new data type and representing a kind of an abstract data type idea. So the topic that we will be dealing with today, and on Wednesday is sets. Okay, is everybody familiar with sets? Okay, what is a good intuitive definition of a set? Everybody throw one at me. Yeah, set of all natural numbers. Okay, but what is a set? Yeah. Okay, an unordered list of things without duplicates. That's a pretty good thing. Unordered uh, list of things, some arbitrary things without duplicates. Okay. Uh, since we are talking about lists, right? I would kind of like to switch the terminology there, because if we talk about unordered lists of things, right? We can say that any individual list is unordered. However, what we mean, or like what is meant there by an ordered list of things, is that we don't, the order really doesn't matter, right? So for example, we could consider this list unordered. Doesn't mean that we consider it a set. Uh, what the important thing is that if we consider both of these lists as sets, both of these lists are the same set, right? So I would say a set is a collection of things without specifying what we mean by collection, but that was a very good definition. I just would like to reserve lists, the name list for things where the order does matter. But we will stay with lists for our implementation. Now, okay, so we have an intuitive understanding of what a set is. It's a collection of things without duplicates where the order doesn't matter. So any way you list the elements of a set, uh, if they are the same things, the sets are considered the same roughly. Now, what are some basic or essential operations on sets? What should we be able to do with any set? And I will just write it down as operations wish list. So we need to know what we need to implement. And I'm getting some things online. Okay, so I'll get one from online. One is union. What is another? Yeah? Intersection. Any Other operations, yeah? Cartesian product, very good. That was also online. I see set difference and complement. What other operations? Yeah? Cardinality, yeah, very good. What else can we do with a set? Yeah? Check membership, very important operations. Okay. Some definitions will even say that a set is anything for which it actually makes sense to ask a question, is an element a member of the set? Right? It's a very abstract definition in terms of like, can you tell that something is a member of a set? Getting an element from a set, so yes, we could say that will be a little problematic. What else? Yeah? We could, yeah, adding an element to a set. We could say that. Yeah? Subsets. So we need to be able to say whether a set is a subset of another set, so whether all its elements are contained in another one. Subset. Yeah? Power set. Exactly. And we also have it online from Onatina. Power set operation. Related to subset, yeah? Partitioning sets. Wow, now we are getting into some. There's one more thing that we might want to, yeah? Set equivalence, exactly. We want to be able to say when two sets are equivalent, and we also have symmetric difference. It's a pretty long list already. Okay. So there's a few things that we might want to do with sets. All of these kind of need to. They assume that the properties of a set are maintained, so that there is only one element, so each element only appears once, and that the order doesn't matter. And on the output, they should also preserve these properties. Let me order things here a little bit in terms of what is good to start with. So checking membership is a very basic operation that we should probably start with. It's very essential for sets. Maybe adding an element to a set would be also good, because that kind of we can use to implement some of these other operations. We have intersection, Cartesian product, finality, subset. Something that we might want to do. And equivalence is also something that we might want to do. Okay. So we have a wish list of operations. Our intuitive understanding was, the initial kind of suggestion was that actually set is a list of elements that is unordered and where each element only appears once. So the first representation that we're actually going to try is to represent a set as a list. Okay, and let's start with a set of numbers. And let's say that we define number set as the list of number. And we say, just briefly, no repetition, order does not matter. Okay. So the most basic operation is we want to check membership of a set. So we want to take a set here and a potential element and return whether the element is contained. Given set contains the given value. Some examples. Actually, first we should do a few sets so that we have some sets to work with. So an empty set, if we use list as a representation, will be just an empty list. Let's do a set of a few numbers. 4 or 2, 4, 6, for example. And let me do 1 as okay, as a few examples, and now contains for set 1, 2, 3. 3 should return true. And let's do empty set doesn't contain any elements at all. Okay. So we have a sketch of a function. I want to check whether the given set contains the given value. So we give it a set, give it a value. We have a few examples. How do we go about this? How do we check whether an element is, or a value is an element of a set? Yeah? We could use a NOR map. Why would we use a NOR map? Yes. So what we are asking is any element of this set equal to this particular value, right? That's the condition we are trying to check. So is there an element in this list or in this set that satisfies the condition that it's equal to this value, which we can express very easily using a lambda by saying 6 equal to value. Okay. We go through the set, through each element of the set, and check whether it's equal to value. If at least one is equal to value, we'll get a true, because we are combining it with OR, the result of the whole operation will be true. Okay. We seem to be good. Is this clear? Any questions? Okay. Let's try adding an element. Let's do add element, which will take a set and a number and will return a new set. The key binding for lambda is command backslash. So let's say that we have the set containing 1, 2, 3, and we add 3 to it. what do we expect back? Sorry? Yeah? Just 1, 2, 3. We would expect exactly the same set back because 3 is already contained. There is no repetition, so we expect the same thing. Let's say that we are adding some element to an empty set, then we just expect to get set containing just that number. Okay, I have a set, I have a value. I'm adding it to the set. What do I do? Yeah? Okay, so I would use append how? So append takes 2 lists, right? We represent sets as lists, yes? Exactly. So we have 2 cases, right? And one of the examples actually indicates this. If we already have an element, we are not actually adding anything to the set. We only add an element if it's not already contained in the set. So we first need to check whether the set already contains the value. If it contains the value, we can simply return the set itself. If it doesn't, yeah? Yeah, or we could use something, yeah? Yeah, we're using lists, so we can just simply prepend the value to the given list, right? The order doesn't matter, we just put it in the front, we're done. Yeah? Damn it. Thank you. Okay. We're good there. Okay, what else is on our wish list? So we did this one, we did this one. Subset, shall we do subset? What's the signature of subset? Yeah? Exactly. We are checking whether one set is a subset of another one, so we are returning either true or false. So we do n set and n set and return a boolean. All right. First set is a subset of the second set. Some examples. So three, of course, one true for this one. Also true. False. How about this example? Good? Yeah? It would be true. Yeah, empty set is always a subset. And how How about this one? Yeah? True, because these two sets are actually the same set, so they're also subsets of each other. They're not proper subsets, what we call proper subsets, so then they would have to be smaller, but they are subsets. Each set is a subset of itself. Okay. So now that we have a few examples, how can we define this one? What is the definition of a subset? When is S1 subset of S2? Yeah? Exactly. When every element in S1 is a member or is contained in S2. How can we express this very nicely? Josh? Exactly. So we can use an Nmap because we want to check whether every element of S1 is included in S2. So what is the second argument? What set are we iterating through? I think I lost that. Yeah? S1, exactly. Again, for each element of S1, is that element included in S2? And so is each element, so for each x in S1, is it contained in S2? Okay, yeah? Sorry? Damn it. Thanks. Okay, and we're good. Again, we're just re-expressing basically the mathematical definition. We're just saying, is each element in S1 contained in S2? And Nmap is a pretty elegant way of expressing that. Any questions so far? Okay. Now, set equality. Let's call this one set equals ha. All right. Check whether two sets are equal. S1, S2. Yeah? Exactly. So two sets are equal if they contain exactly the same elements. In other words, two sets are the same set if they are subsets of each other. So if S1 is a subset of S2 and S2 is a subset of S1. Okay, we can just write a few expect this one to be the same. Okay, let's check. We're good. So we have subset, we have set equality or set equivalence. Now let's combine sets. Union takes two sets and returns a set. All right. Produce a set which contains all elements from both sets. For example, and what is the union of these two sets? Josh?
How is this different than checking like the same function we take into n sets and the output n set? The output n set only contains the elements that are both that are in both sets.
Come again?
So how is that different? How is this like union function different than like a function that outputs a set of all elements that are only in both sets?
Only in both sets. Well, that's a different operation. What is that operation called? Yeah? Intersection.
So this just like puts them together?
Yeah, union unifies both sets by taking all elements and getting a set that contains all the elements from one set and all the elements from other set. Of course, non-repeating, etc. Intersection is the one that only contains the elements that are both in both sets. Okay, so we'll get to that one. So what is the element of this set? Element, union. Josh? Set 1, 2, 3. Okay. How about this one? Yeah? 2, 3, 4, 6. Okay, so one contains 2, 4, 6, the other contains 1, 2, 3. If we put them together, we should get a set containing these elements. And one last example. Let's take set into one empty set. Yep. Set 3, 2, 1, right? So union is the identity of, sorry, empty set is the identity of union. So whatever we unify with an empty set returns itself. Okay, we have a few check expects. Let's get down to implementing this. How do we compute the union? Yeah? Add one set to the other set and subtract the intersection. I don't think that's union. And we need something more basic. We didn't define intersection. We didn't define set difference. How can we? Any ideas? Yeah? That's a good question. How can we even know what the order is? Yeah. So is there something that I maybe need to fix in my check expects? Yeah?
We should probably define like set equivalence to check it. The first thing is equivalent to spectrum. Because for check specs, the order would not have.
Yeah, so when we are check expecting, we are matching exactly, so the result of doing this needs to match exactly this, right? But even if it's reversed, we no longer get true, right? So the equality that check expect uses isn't the equality that we want to use. And as you said, we need to use set equivalence, right? Which we just defined. So what I actually need to do instead of doing this is to check whether my set equality returns true. Okay. Using just check expect whether the union returns something like this makes it very implementation specific, right? And it's not actually the property that we want to check. What we want to check is that the union of two sets is equivalent to this result rather than exactly equal. All right. Very well spotted. Good question. Okay, but how do we actually define union? Yeah?
We run filter on one of the set and remove all common items.
We run filter on one of them, remove all the common items, and then add them together. But if we remove the common items, then this wouldn't be the same set, right? Ah, okay. So your idea is basically to use append, remove all the elements that are in this set from this set, and then simply appending. Right? Okay. So append S1 over, and you suggest filter, right? And X, and we are removing from S2. Well, not removing. What are we keeping? So what are we keeping? What is the lambda, the body of the lambda here? Josh? If not contained X in S1, exactly. So we append the first list to a list that results from removing all the elements that are contained in S2, in S1. Right? We take S2, throw away all the elements that are already in S1, or in other words, we are keeping only the elements that are contained we are keeping only the elements that are not contained in S1, and then we append them together, which is a good definition, and it works. Okay. There's another way of defining it. Can anybody think of another way of defining it? Shy. The filter part of that is just the difference of sets, yes. So what we are computing here is actually the difference of the two sets. What is another way of defining it? Can anybody think of something? How about using foldr? the way we can think about it is we start with S2 and start adding elements from S1 if they are not already contained in S2, right? So another way of defining this is we start with S2, right? And we go through S1, set of numbers, or otherwise in our representation a list of numbers. And we want to add each element from S1 to S2 if it's not already contained. What do I need? Josh? Sorry? Not append, because each element of S1 is an individual number. It's not a list. So something like this. So we take an element. If only I had a function that does that. We just define a function that does exactly that. If the value is contained in the set, do nothing and just return the set. Otherwise, add it, right? So all we need to do is actually just fold add element, and let's just write out the types so that we see how it fits. So this is a number set, or otherwise list of number. This is a number set, and this is a function that takes a number set, no, an element. How did I write it? I wrote it the other way. So we actually need to reverse the arguments here. So x set, and we add element set x. That was an oversight. And set okay. Add element otherwise does all the work for us. It checks whether x is already in the set. If it's in the set, it will just return set, so it won't be added, and otherwise it adds it to that. So let me just check that I didn't introduce errors and whether this works. Yes, of course, typos. Okay. So these two are equivalent ways of defining a union. So why don't we take the difference of the two sets? So removing basically from one set, we remove all the elements that are contained in the other set, and then we simply append it, right, to satisfy the condition that there is no repetition of elements. That's one way of viewing it. The other way of viewing it is basically going through one of the sets and keep adding elements from it to the other one if they are not contained already. And this is exactly what add element does for us. Okay? The only thing I needed to do is to flip the arguments with the lambda. Okay. Does this make sense? Are there any question? Okay. Now we get to intersection. Again, two sets. Returns a set which contains elements common to both given sets. Okay, so, and I know that I need to use my my set equals. So if I compute the intersection of set 1 to 3 and set 3 to 1, what will I get? Yeah? Set 1 to 3, exactly, or set 3 to 1. Okay, check expect, set equals, how about this one? It's the intersection of 1 to 3 and 3 to 1. Shy, 2, exactly. We just get a set that contains only 2. What about the empty set? Yeah? Empty set, exactly. So the intersection of any set with the empty set is just the empty set because they have no elements in common. And let's do 3 to 1 and a set of just 5, which will also be the empty set. How do I compute the intersection? Yeah?
So we could use a filter with containers.
Could use a filter.
One of the sets and filter it with a lambda checking if that element is contained in the second set.
Okay, so we can pick one of the sets and we want a lambda that takes an element and checks whether X is contained in the other set. Exactly. Filter. Lambda is here, and we're done. Right? So the intersection is basically just going through one of those sets and only keeping the elements that are contained in the other set, throwing away all the elements that are not contained in the other set. Thank you. Okay, still with me? Okay, intersection, give me all the elements of S2 that are also contained in S1, and that's the intersection. Okay, so we did union intersection. I actually want to do Cartesian product. We know how to do set difference as well. We kind of did it in our union when we used append. I won't go through that, so we kind of have that. Now, how about complement? Complement is an interesting operation. How would we implement complement using a list representation? Charlie?
So in order to define the complement, we need to define some kind of universe. So we need an argument, but it just becomes a difference problem.
Exactly. So our problem with our list is that complement is basically all the elements that are not contained in the given list, right? And if we need to return a list, that means that we need to collect all the elements that are not in the given set. But because we are using lists to represent, we need some sort of context, right? What are the other elements that are not in the given list? And once we get there, we need to add an extra argument, and this just becomes set difference. Okay, so actually the other representation that we will look at later or on Wednesday will allow us to define complement, but with lists it becomes a little problematic because we need to know what are the other elements that we are considering. A good one. Cardinality with lists is really simple. We just return the length of the list, right? Selection. So somebody suggested that selecting an element from a set is an operation that we do, and quite often when you do mathematical reasoning, you just said like just some element from this set, right? And in this case, we could basically just say, okay, just give the first element or give the last element. Power set exercise if you want to. It's kind of fun. Partitioning and symmetric difference. If you want to do that, then come here too. But what I want to concentrate on is actually computing a Cartesian product of a given set. Okay, so just that we are on the same page. What is a Cartesian product? Yeah?
It's a set of like sets in which the first, it's like kind of hard to explain. It's like the first element has to come, so it's like two sets, so it's A times B.
Mm-hmm.
First element within, it's a, no, it's a set of subsets, and one of the subsets, the first element comes from the first given set, and the second element is given from the second given set.
Mm-hmm. Yeah, there's just a little terminology thing. So we talk about subsets and talking about the first and second element, right? Sets are unordered. So instead, the kind of the data type that we use in math is we compute all the pairs where first element of the pair, because a pair is ordered, right? 1 and 2 is different to 2 and 1. Or 1 and A is different to A and 1. So the Cartesian product, let me write it, but otherwise the definition is pretty good. I'll use X as the thing. So Cartesian product is basically computing all the possible combinations where the first part of the pair is from the first set and the second element of the pair is from the second set. So it's really just 1A, 1B, 2A, 2B, 3A, 3B. Okay. So we combine all the elements from both of the sets and get all the possible combinations. That's a Cartesian product. Okay. And kind of the idea here is when we talk about Cartesian coordinates, right, where one of these sets is the numbers on the x-axis, the other set is the numbers on the y-axis. So the Cartesian product of all the axes is actually the set of all possible coordinates, right, on a plane. Okay, so we know what a Cartesian product is. Now, what is the signature of the function that computes a Cartesian product? Charlie?
So it takes in two number sets,
Yeah.
but the output is some set of pairs.
Exactly. So our problem here is that we don't have actually the definitions that are required to express what we want here, right? And what we could do is one solution is to just set a set of A pair set is a, let's say, list of pair of number pair set. Something like this. Or let's just think about how we can get a generic definition of a set. I will just create myself a new file and kind of try to do the following. So instead of having a set of numbers, right, where we just use the list of numbers, we'll try to make a generic data type similarly to how we have a generic data type of list of arbitrary elements, and we'll just say, well, a set of things is just a list of things. Okay. We'll say it really doesn't matter if we are using numbers. So now, from now on, this should also be a set. All right, and this would be a set of string. Etc. Now I'll do an advanced operation where I will simply search and replace all the possible occurrences of number set to set of x, and we will check the validity of this right away. No, I don't actually want to replace. I don't want to skip them. Okay. Let's try again. Okay. And then everywhere where I had a number, I will simply put x. Okay, except for this one, this one. Replace, 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 replace. Okay. So I replaced the signature, and I need to fix them by introducing the variables. Is there something that I'm missing here? Is any of these operations actually, does it care about whether I have a set of numbers or I have a set of arbitrary things? Because like when I look at intersection, for example, that's just defined in terms of contains. Union is defined in terms of add element. So if I am able to add an element, that's fine. Set equals also doesn't seem to refer to anything specific. As long as subset is okay, subset uses contains. Is there something that prevents me from doing this general thing? Yeah? Exactly. This equal sign is specific to numbers. Right? So we have a little hurdle there. I can generalize, but I need a notion of equality that works for arbitrary data types. Now, at this point, I will do a no-no, and I will use equal. Okay. However, this is a bad solution. It's a bad solution because I would lose points if I submitted this. But there's an actual reason why this is a bad solution. Can anybody guess what is the problem here? With equal. It works fine for numbers, it works fine for strings, it will work fine for sets of posons. Yeah? It will work for Booleans. I have sets of arbitrary, very good question. So David is asking, would it break for custom data types? Which is a good question. As I said, it would work for posons, it would work for any struct that we define. But what if I want to have a set of sets? Right? I have a, if I write a set of sets, so I will say, okay, list is a list of 1, 2, 3. Okay, so this is a set of number in my representation. Now, if I want to ask a question like, and let me say, something like this. If I consider this list of lists a set of sets, then this should return true, right? But it doesn't unless we force it to use a custom equality of sets. Right? So equal will fail us in this case. So this is where equal is really problematic and why we want to avoid at all times. Because we either want to be specific, we are comparing only numbers, and it should fail if you give me something else, or we should have a quality where things just cannot fail because you somehow forgot that it doesn't work for custom data types. Okay. But for the sake of this lecture, I will stay with equal, okay, even though it's problematic. So now I am able to have a set of arbitrary things. So I can say a set of pairs of sex, okay, and let me just define myself a little helper struct, which I will call a pair, and I will give it first and second, okay, and a pair of x and y is just a pair of, it's a make pair x, y. Okay, now I have a way of writing down this signature. Here's another question. Is this the most general signature we can get for Cartesian product? Do we really need to have the sets, two sets of the same type? Josh? Exactly. So just like here, I actually used a set of numbers and a set of some symbols, right? In my signature, I can express this by saying, I don't really care what the elements of the first and second set are, because I can now say that I'm just combining them into pairs of these different types. So we're good there. Let me do a check expect for this one. I learned and I'm using my set equals. Let's do set 1, 2, 3 and a set of A, B, so that we have something that looks like the example that I wrote above. And this would be a set or a list of make pair 1, A, pair 1, B. Mhm. 2 and 3 and 2 and 3. And we expect this to be true. Okay, so that's an example of how Cartesian should work. If we give it a set containing 1, 2, 3, and a set containing A and B, a set of numbers, set of strings, we should get a set of pairs 1A, 1B, 2A, 2B, 3A, 3B. Now all that's left to do is the little detail of how do we define this. We probably won't get through the whole thing, but are there any ideas how we can approach this? Yeah? Uh-huh. Uh-huh. So we basically want to, so we already, as you're saying rightly, that we want to go through each element of the first set, right? Whatever is there. Kind of take each element, hold it in one hand, and then go through each element of the second set and make pairs as we go along with the element that I'm holding in my left hand, right? So I pick 1 from the first set, and then I pick A and B. I pick 2, A, B, 3, A, B. All right. It almost sounds like this operation of holding this one element and taking the elements from the other set, almost as if I'm mapping this operation over the elements of the first set, right? If I have an operation that takes an element X from the first set and somehow makes a pair where the first component is X, we just need to get the Y's from somewhere, then I can simply say, oh, yeah, let's just map this over, let's say, S1. Now, all I need to figure out is where this Y comes from. For each element of S1, I want to take each element of S2 and make pairs. For each element of S1, I want to take each element of S2 and create the pair. this might be a little step too far, and unfortunately, we are right at the end of the lecture. But basically, what we are doing here is going, right? We are mapping over S1 the function that for each element then will produce two pairs for this example, right? The function will take one and then take each element of S2 and form a pair out of this one, right? 1A, 1B. Then it will take 2, so the X will change to 2, and will take 2A, 2B, and 3, 3A, 3B. Yeah? Come again? Yeah, very good. So there is one problem with this solution. That is that it fails. First reason is because I don't close my functions properly. And still don't close my functions properly. No, this is here, this one's here, and now we should be good. Okay. You don't see it here, but the reason why this fails, let me just show what we produce here. Is that instead of a list of pairs, because of the restriction that actually we return a list of the same length, we produce a list of lists, right? Where the outer list is for each element of the first list, create a list of pairs with that element as its first argument, right? So the first list are all combinations with 1, the second list are all combinations with 2, the third list are all combinations with 3. Okay. So, yeah?
Solve this problem by just using Foldar and appending all of these lists together into one list of pairs instead of list of those pairs.
Exactly. All we need to do really is to flatten this list, right? Take all the lists and just append them together, and we can do this by Foldar, okay? And I will just write it out. You can view it on your own, and I will start with it empty. Start with this next time so that we kind of start from there. Okay. Do take a while with it. This is kind of a little bit more of an abstraction, this combination of map and having a lambda that actually uses a map. So we'll start with that next time. The other thing that you might want to think about is how do we represent, no, please don't. How do we represent sets such as all even numbers? Is our representation actually suitable to represent something like this? All even numbers, all positive integers, all strings longer than 5. Okay. Thanks for coming. Thanks for listening. And I'll see you on Wednesday, I hope. Okay. Good luck to us all.